Okay, so this is just a review really in many ways, and we're just going to explain and start to talk about the rationale behind it. But we've discussed nucleophiles and nucleophilicity, which once again I still say would be an awesome geek chic rock band name. We have to have something that we just use as a generic marker. You know, things can be better or worse. So if we say water or alcohols can be nucleophile, they have lone pair electrons, right? I mean, so the trend is these are better. Carboxylic acid is worse. And that should make sense. The problem with the reason why the carboxylic acid isn't as good. See, it's got lone pair electrons. But if you remember, let me change colors here. There's resonance. Boom, boom, boom. So there's resonance between these. And anytime, right now, before I completely shatter your belief system, because you're going to find out later on that there is a time where resonance actually decreases the stability, but 99.999% of the time, anytime you have resonance, it increases your stability. So there's resonance structure between that. And so because of that resonance, it's not like those lone pair electrons are always located in one location or another, and so it's just a weaker nucleophile. And we'll discuss the trends for these other things, later. We'll talk about the reason why that's true. Okay. So nucleophile means love the nucleus. Whatever it attacks, it's called an electrophile, which I don't think is on that one, which means it loves the electrons that's coming in. And by far, and I usually say lone pair electrons on something that's either negatively charged or delta minus. Okay. So this one's, you're going to learn how to name this later on, but this is dimethyl sulfide. It answers that call of being a nucleophile. It's got the lone pair electrons. It can come in smack, like what we've talked about before. The methyl group of the iodomethane, iodine can leave. Knowing what you know now, is this going to go SN1 or SN2 reaction mechanism right here? SN1, because it's a primary. Well, actually, it's not even primary. It's a methyl halogen, halide, and so it's got to go SN1. It has no friends to help it out. And then we get this cation. It's called trimethyl sulfonium iodide, but that's beside the point. Okay. All right, and so nucleophilicity, I know they talk about the kinetics. So if it's more nucleophilic, it means it's going to be able to do it more quickly, okay? And I hate the way they have described this. It has to do with basicity, with quirks. I wouldn't use that term. What I like to explain it is, think of nucleophilicity on respect to the periodic table. You have to consider, are we comparing things on the same row, or are we comparing things on the same column? Just like we did with something that made a stronger acid or base. Okay, that's the way that I prefer talking about it, versus saying know the quirks or what have you. Okay, so how does that refer? If we look across the row, that's the important part here. As we go across the row, they say it goes with the basicity. Remember, the bases, typically they're going to accept hydrogens. That was the simplest term. Remember, we always say acids donate protons, bases accept them. Well, a base, if you think back to Lewis bases, what that means is they have lone pair electrons and can go and attack things. And it should make sense. I don't know why they did it this way. Oh, whoops, I thought I had... That's supposed to be a bullet point. Okay, that's not a minus charge or anything out there. Okay, that's a bullet. Let me do that. Bullet point. Okay. And it should make sense. Remember, carbons do not like to be charged, whether negative or positive. They prefer not to. So it should make sense here that the methyl carbanion is going to be more reactive than fluoride F-. Okay, this is a much stronger base than this one. Okay. Whenever this goes in attacks, it's going to be adding a methyl group. This will be adding an amine, an alcohol, so on and so forth. However, when we go down on a group, go down on the periodic table, that's the quirk that they were talking about. And so that's why I don't like saying just memorize it according to basicity, because it's the opposite trend. So don't follow that example right there. It's true with basicity with respect to the same row in the periodic table, but going up and down, it has to do with the polarizability. Remember the jiggle factor here. Which should make sense. Because remember when we talked about iodine, remember its huge electron cloud. Remember iodine was the best leaving group, but it's also the best nucleophile of the halogens. Because it's so fat, it's got a bigger jiggle factor, a bigger polarizability. So because of that, it's easier at any one point in time for more of the electron density to be on one side versus the other. So that's why it makes it a better nucleophile. Okay. And finally, they talk about solvation. If it's really small anion, it can be more easily solvated. Just means more water can hang out around it to kind of keep it and protect it from being able to go and attack things. And so that's the reason why chloride is worse than bromide, which is worse than iodide as well. That's just another thing. Can you imagine like all the water? It'd take a lot of water to try to block a big old fat iodine. Okay. So that's what's bringing us back to this table when we're comparing these. So sulfur is better than oxygen because it's further down on the periodic table. It's more polarizable. It should make sense that OH minus is better than H2O because it's going to be even more. It's an even stronger base, so on and so forth. For whatever reason, the book decided to redo and put this in here in this location once again. The SN1 mechanism, but it's a good review, so that's why I left it in. So for the mechanism, first things first. I think this will let me move it down. Oh, awesome. You can do SN1 mechanisms with alkyl halides, just like you did with the alcohol, except that first step is a little different. Whenever, and this is just a kind of a generic rule of thumb that you can remember, almost always, I'm sure there's probably some exceptions, but almost always when we start with alcohols, they're acid catalyzed. Remember, you protonate first. With alkyl halides, they are not protonated, because that would make them an even worse leaving group. So that's why, if you notice, there's not a protonation step here. Usually, if anything, it's under basic conditions, but it's definitely not under acidic conditions because we need that bromine to leave with the two electrons. So you have to add energy. You're forming that carbocation. So now we've fully formed that carbocation, and you can go ahead and go from an alkyl halide to an alcohol. But to do that, what happens is that water, or one of the waters here, is now the nucleophile that comes into the carbocation. And so now we've made this alkyl oxonium ion. And for the final step is you've got to get rid of the extra hydrogen. And so the bromine, or technically another water, because remember hydrobromic acid is a strong acid, comes and takes off that extra hydrogen. So now we ended up with our alcohol and HBr. So it really is the reverse of what we saw before. Yeah?
On an exam, if we were asked to show a mechanism, is that the way you want it to look, like with the energy diagram and everything?
No, I would ask for an energy diagram, And because actually if you look at this doesn't show the mechanism, it shows the transition states. Mechanism is when you actually put in the arrows and you draw it in. And if you need to do the sound effects of boom, feel free. It always helps me. It makes me feel better. Okay. So SN1 is unimolecular. It's the tertiary alcohols always will undergo SN1. Tertiary alkyl halides undergo SN1. Most of the secondaries will also undergo SN1. Okay. And because of that, remember when we did it with the alcohols, the rate was, there's always that little K, but the rate was due to the concentration of the alkyl oxonium ion, which had to do with the alcohol. Here, it's going to be, the rate's going to be due to the tertiary alkyl halide, which makes sense because that Br is what has to leave in the rate limiting step. Anytime that you're forming a carbocation, it's rate limiting. It's a slow step because they do not want to be positively charged. Okay. All right. And yeah, all the other stuff we talked about. So that's the coordination. Okay, so this is a really special condition. Or not condition, special name, I guess, if you want to think of it, for SN1. When it comes to SN1 reactions, weaker I can say that now. Weaker nucleophiles are better in the sense that since they typically are weak, they can undergo an SN1. When we do the elimination reaction, if you have such a really, really strong nucleophile, it tends to go under elimination, and I'll explain that reason why later on. Okay, but that's a different chapter. It's just because it's easier to take off the neighboring hydrogen than it is to go in and attack that quarterback. You know, why go for that quarterback when you can just run over and, you know, run over the little hydrogen next door to it, and so it takes that hydrogen instead. But I can think of a few examples, but they wouldn't be very nice. It's kind of like Red Rover. Let's do this one. So, you know, if you're going to Red Rover, I don't know if you kids ever played, that's why I can say nice, I'm a grandpa. But if you ever played Red Rover as a kid, you know, and you said Red Rover, send whatever, right over. Well, you know, if you're smart and you're going to go over there and attack something, why go through the big guns there? You go and you hit that little kid that's over the corner, the one that's like, don't come my way, you know, that kind of thing. That's the one you take out. Because you're big old strong, you know, nucleophile. Why go after that one when you can guarantee to take the little kid out? I told you it wasn't necessarily nice, but that's what happens in an elimination reaction. Okay, but solvolysis can occur. Solvolysis just means it's the solvent that's the nucleophile. So ones that do this a lot are water. Okay, so that way you can go from an alkyl halide to an alcohol. Ethanol or methanol, which are alcohols, okay, they can undergo that because they're usually really good solvents. And ammonia. Is ammonia not? They don't have ammonia listed, but ammonia can also do it as well, right? Because it makes an amine. Because those are good solvents, they have lone pair electrons, but they aren't super strong nucleophiles because they already have hydrogens on them and things like that. So why... You know, it's the more the peace-loving kind. So they can undergo SN1 reactions better. Here I can even do an example. So, well, actually, we already did the example. That example was with water coming in to do it for the alcohol. So if we had something like, just that way I'll take it through step by step. We had our make it a little different. And we had water. And a lot of times for solvolysis, they don't even, it's kind of tricky. They almost get you because the question may be worded and say, you know, and it's usually at lower temperatures because you're wanting the bromine to leave first and order the nucleophile then to saunter on over. So they may just tell you like a low temperature and in water. So what's the product going to be? Or something in, you know, methanol. And actually, why don't we do methanol instead? That way you can see like what it looks like instead. I mean, it's the same mechanism. It's just that way you see something that's a little different. Okay, so the first step is the rate limiting step. So it's slow. And once again, that's where the bromine leaves and takes the electrons with it. takes those 2 electrons, so ultimately you can form that carbocation. And technically you have a Br minus. It can be reversible, like it can go backwards, and that's one of the reasons why I put that. If it goes backwards, you're just going to get your, your alkyl halide back. But there's so much of since this is a solvent, there's like a gazillion methanol molecules around and just a little bit of the bromine. And so that's why if you wait long enough, the odds can be in your favor. And so what do we have over here that can be the nucleophile? What are the 2 possible nucleophiles that we have in this reaction? One of them's the bromine, but what's the other one? The oxygen. And so that's exactly what happens. Now, I don't want to have to redraw it. I'm going to be lazy. This comes in and it attacks the carbocation. Okay. And then we're going to end up, in this instance, and this time I won't skip any steps. Biochemistry loves to skip this kind of step because they're like, oh, it happens so fast. Like it doesn't. The deprotonation step is what I'm saying. Because now what happens here is we've got this alkyl oxonium ion, and since methanol was the solvent that we started off with, it's going to be another methanol that comes in to take it, which is what the book shows a lot of times. If it was water-based, then it would be water that comes in to take it. But it just comes in, it takes off that extra hydrogen. Technically, it's also fast and reversible. Okay. And then there's the shortcut method. And you end up with one of the solvent molecules, being protonated. But that's it. That's the mechanism. I said it's nothing brand new. Okay. Not earth-shattering in that sense. So, anytime that we're doing these SN1 reactions, and we mentioned this multiple times, that this is just, they're better at drawing the pictures of it than I am. We end up with that planar intermediate. And at least in theory, the nucleophile could come in either from the back side or the front side. And so you would think 50-50. There are some reactions that's closer to 50-50. But regardless, you're going to end up with a racemic mixture, okay? Now, what they like to talk about here... Oh, what happened there? What they like to discuss here is this idea of partial inversions, which like I said, I hate that term. It is true that because of it, that since this has to leave, it may be kind of hovering around. It's not completely gone, but it's not a true 100% backside attack either. And so that's why don't memorize, it's 89-11. The important thing is you start off with 100% R, and you're ending up with a racemic mixture. Okay, sometimes that may not be a big deal. Sometimes it is. It depends on what your whole goal was. Okay, and so that's why I just wanted to point out the fact, they talk about, especially the bigger the group is, the more of this partial inversion, but in reality, versus if it's something really tiny, then it's going to be, it's going to tend to go SN2, so therefore it's going to be 100% inversion. Right. But regardless, we start off with 100% R. We now have a racemic mixture. We got a mixture of it. That's the really important thing there. I would never ask you in class, at least, or on the exam, the evening exam. So, what is the exact number of this? Well, I wouldn't expect that. If you got it, that'd be like guessing the number of gumdrops in the big jar at a fair or something like that. Okay, and this is just showing, once again, how it's possible and using the little space filling. Okay. And then finally, we've already talked about this, but just like with alcohols, we can still get rearrangements with alkyl halides undergoing substitution reactions. Do you remember when did you have to expect the rearrangements to occur? When did it happen a lot? Whether it's a methyl shift or a hydride shift. When did you expect it? All the way back to last chapter. Like I'm going to draw a couple of examples here. Which one of these? Oh, wait a minute. I didn't do it quite right. I want to hopefully make it a little bit more obvious. The one on the left or the one on the right? Which one's going to be more likely to undergo some type of shift or rearrangement? The one on the right. And the reason why is anytime, whoops, I meant to do the little arrow. Anytime that you've got it on the primary, to where if it's here, it'd be a hydrogen. If a hydrogen came on over, then instead of being a primary carbocation, we now make a secondary carbocation, which is more stable. Okay. Here, this one's a tertiary. It's not going to undergo a rearrangement, right? Because whenever this leaves to make the carbocation, it's perfectly happy as a, well, I shouldn't say perfectly happy. It's more happy as a tertiary carbocation than if the hydrogen came on over here and we would have a secondary. So remember, anytime some examples would be if your functional group, oh, whoops, I thought I was writing. Was alpha, which meant next door, was alpha to, for example, a quaternary carbon or even a tertiary carbon. Oops, that's supposed to be tertiary. Tertiary carbon, you can expect those rearrangements, so shifts. Okay? And the reason why is the intermediate form, remember we had the rule of thumb there, the intermediate that you were forming was more stable than what you were starting off with. So if it's a quaternary carbon that you're next to, then it's going to be a methyl group. If it's a tertiary carbon, usually it's going to be the hydrogen because it's easier for the little hydrogen to come along, okay, with the electrons. You can get some with secondary carbons if what you had started off with was a primary. Like a hydrogen could come off over and you can get some weird things then. But you really expect it here and here. And remember, alpha just means adjacent to. So I like to always refer to, so for example, so I refer to this as being the ground zero, which is not the technical term, but ground zero carbon, because it's the one that the functional group is attached to. So therefore, this one is called the alpha, because it's next door to it. By the way, does anyone know what this one, the one that's 2 down, is called? Beta. Alpha, beta, gamma, delta. You know, it goes according to the Greek alphabet. Okay, which, yeah, they use that a lot of times in biochemistry too. And then, yeah, it goes on and on and on. But in organic chemistry, these are the two that we talk about the most, are alphas and betas. Okay. All right. Okay, so